In modern gold processing, you are moving mountains of crushed rock just to extract microscopic fractions of a single element. The margins are razor thin, meaning the chemical process you use at this exact stage dictates whether the mine makes a profit or goes bankrupt. Right now, cyanidation is the undisputed king of this process. It is used by over 80% of all gold mines operating globally. The industry relies on it because it is highly economical and unparalleled in its ability to selectively dissolve gold, separating it from gangue and waste rock. The primary catalyst driving this entire system is a chemical called sodium cyanide. But that efficiency comes with a massive liability. Sodium cyanide is lethally toxic. Transporting it requires strict security protocols, and the resulting waste slag creates an environmental hazard that can persist for decades. Because of these risks, states and countries around the world are implementing rigid wastewater regulations and, in many cases, outright banning the use of cyanide in extraction. This chart maps gold processing methods by toxicity on the vertical axis and efficiency on the horizontal axis. Older extraction methods sit down here. Sodium cyanide sits way up here, high efficiency but extremely high toxicity. That leaves this crucial bottom right quadrant completely empty. Plant operators are trapped. They desperately need a low-toxicity solution to survive tightening regulations, but they cannot afford to adopt alternatives that tank their recovery rates. Recently, a new class of eco-friendly gold leaching agents has entered the market to fill that gap. The most prominent alternative currently being deployed is JIN CHAN metallic ore dressing agent, but plant operators and metallurgists hear eco-friendly and immediately worry. In heavy industry, going green is frequently assumed to mean weaker chemical performance and lower profit margins. So we are putting the marketing claims aside. We are going to look at a rigorous head-to-head operational comparison between traditional sodium cyanide and the JIN CHAN agent. We need to answer the only question that actually matters to a plant manager. Does complying with environmental regulations mean sacrificing your gold yield? The first hurdle any operator looks at when changing chemicals is capital expenditure. Does adopting this agent require tearing out pipes and retrofitting the processing plant? Let's look at the standard cyanidation flowsheet. It relies on three main stages: dissolving the gold in a tank, capturing it through carbon adsorption columns, and pulling it out via an electrowinning cell to form gold mud. Under standard operations, sodium cyanide is introduced right here, at the dissolving tank, as the primary leaching agent. The eco-agent drops directly into this exact same process. Every tank, column, and cell stays exactly where it is. Financially, this means a plant can transition to the new agent with zero capital expenditure on new processing equipment. The only required inputs are running baseline lab tests on your ore and retraining your staff on the new, safer chemical handling protocols. From an infrastructure standpoint, achieving full environmental compliance does not require rebuilding your plant. But infrastructure doesn't mean much if the chemistry fails. Let's look at the raw metallurgical data from a comparative test conducted across 6 distinct gold ore samples. These samples included oxidized ores from Sultan Kush, as well as a variety of mixed ores, oxidized ores, and gravity separation tailings pulled from mines in Tanzania. This matrix compares both chemicals under identical leaching conditions. We are evaluating required dosage, leaching rate, carbon adsorption rate, and overall cost. Starting with the input, both chemicals require virtually the exact same dosage of agent per ton of processed ore. Moving to the output, the eco-agent matches cyanide in both the speed at which it dissolves the gold and the volume of gold adsorbed by the carbon. Because the dosage and yield align, the overall economic footprint per batch stays steady. This grouped bar chart illustrates the final gold recovery percentage across all 6 sample types. Across heavily oxidized rock, mixed ores, and processed tailings, the results show consistent parity. Of course, in practice, no 2 rocks are identical. Your exact decimal point efficiency will fluctuate slightly depending on the specific geology of your primary ore, but the aggregate metallurgical data clearly dismantles the myth that avoiding cyanide requires taking a massive hit to your recovery rates. Operationally speaking, it is a statistical tie. If cost and yield are effectively tied, operators need to understand the actual trade-off they are making when considering a switch. The effort input is strictly analytical. You must take time to request lab samples, run bench tests, and verify the chemistry against your specific rock. The output is the complete elimination of lethal toxicity from your supply chain, your storage facilities, and your waste slag. That change alters your business risk profile. It removes legal liabilities, eases transportation logistics, and eliminates the constant threat of a state-mandated plant shutdown. You are simply exchanging a few weeks of rigorous laboratory testing for the long-term operational survival of your mine. The data proves that switching to an eco-agent is a viable one-to-one operational swap, but how quickly you should adopt it depends entirely on your specific regulatory environment and your ore type. This decision tree maps Renette's steps. Are you operating in a jurisdiction with tightening cyanide regulations? If facing strict bans or standard oxidized tailings, you are an urgent adopter. Switch immediately to maintain recovery rates and future-proof against regulatory closures. If regulations are lax, but you process complex, untested primary ores, you are a cautious optimizer. Your immediate next step is securing lab samples to confirm empirical parity before committing. The global extraction industry no longer has to choose between metallurgical efficiency and environmental safety. The chemistry has caught up. The right decision now is simply determining when and how to validate the data for your own mine.